All right, this video covers section 4.4, and here we're going to be looking at logarithms for the first time. Okay, so we've been studying the exponential function already, and that would be a function of the form f of x or y equals a to the power of x. And we know that that function is 1 to 1, so that means it has an inverse that would also be a function. Okay. Now, if I try to find that inverse, I would switch x and y around, and that would give me this equation, x equals a to the power of y. But then when I go to solve for y, that's difficult to do because y is an exponent here. So for this reason, we give this inverse equation a special name and definition. It's known as a logarithm, okay? So the logarithmic function to the base a, where a is greater than 0 but not equal to 1, which is the same as it was for the value of a in an exponential function. So this is denoted with this equation, which is read as y equals log to the base of a of x. Log to the base a of x. And that would be true if and only if x equals a to the power of y, okay? So understand that these two equations are equivalent to one another. The one on the left, we would consider this as logarithmic form, and the one on the right would be considered exponential form. Okay. And again, the underlying idea here is that these equations, they represent the inverse of an exponential function, okay? Since they are the inverse, that means their domain and range can be found just switching the domain and range of the original exponential function, okay? So that would make the domain any value for x greater than 0, any positive value. And then the range would be all real numbers, okay? I also want to draw your attention to the fact that when we're in this form, y equals log base a to the power of x, notice what y represents here. It's an exponent, right? So that tells me that a logarithm is really just equivalent to an exponent, okay? All right, so let's work through some different examples here. The first thing we want to be able to do is just make sure that we can convert back and forth from logarithmic form to exponential form and vice versa, okay? So at the top here, we have a couple exponential equations. We want to change them to logarithmic form, okay? A to the power 4 equals 24. This would be equivalent to log base A of 24 equals 4, okay? And kind of give you a visual on being able to convert here. What I've found helpful is I always start with the base, and I know I take the logarithm to that base of this number 24, and then I equal it to the exponent. So there's kind of like this circular rotation going here when you convert to logarithmic form. For the next one, 3 to the power of m equals 12. That would be the same as log base 3 of 12 equals m. So once again, we have this kind of circular pattern here. I start with the base 3, I take log base 3 of 12, and I equal the exponent of m. All right, now let's go into the other direction. Here we have two logarithmic equations that we want to put into exponential form. Log base 3 of 5 equals c. That would be the same as 3 to the power of c equals 5. So once again here, I kind of have this circular pattern at play. I started with that base of 3 in the logarithm, raised it to the power of c, and equals 5, and 5 is known as the argument of the logarithm. okay? All right, now in the next logarithmic equation, we have log r equals 3. And what I want you to notice is that there is no base written for the logarithm. Whenever that's the case, it's understood that the base is 10, which is what I have written down here in red. So log base 10 of x is equivalent to just saying log of x. And this is known as a common logarithm, okay? It's kind of like if you have a variable of x, you know that the power on that is 1 without it being written. Okay, it's just understood, right? So same idea here. When you have a logarithm with no base, it's understood to be a base of 10. And the nice thing about common logarithms is they are programmed within your calculator. There is a log button on your calculator that is representing the common logarithm, okay? So I'm going to insert a 10 right here. And if I want to go to exponential form, then that means this would be equivalent to 10 to the third power equals r. Okay. All right, moving forward, find the inverse of each exponential function. Be sure to solve for y. So we've just defined a logarithm to be the inverse of an exponential function. So we know that when we're all said and done, and solve for y in both of these inverses, they should in fact be logarithmic functions, okay? So y equals 3 to the power of x minus 1. Of course, the first thing I would do to find the inverse is I would switch x and y. And then in order to solve this for y, I'm going to need to put it in its logarithmic form, okay? So that would be log base 3 of x equals y minus 1. And then, of course, to get y alone, you would add 1 to the other side. And then I'm just going to kind of flip everything here. I'm going to write this as y equals log base 3 of x plus 1. And that would be my inverse function. Okay. For the next equation, f of x equals 4 to the power of 2x plus 1. We know f of x is the same as y, right? So I'm going to begin by switching the positions of x and y. X equals 4 to the power of 2y plus 1. I'm going to go from exponential form into logarithmic form. That would be log base 4 of x equals 2y plus 1. All right, and then I'm going to subtract 1 from both sides. That's going to take me to log base 4 of x minus 1 is equal to 2y. And then I'm going to divide both sides by 2. And I'm going to write this in a special way here. I'll say that y is equal to 1/2 times log base 4 of x minus 1/2. And there would be my inverse function. And of course, you could use inverse notation here, right? Instead of a y, you could also have the inverse of f of x. Okay. All right, we keep rolling. All right, now here we're trying to evaluate each logarithm. Okay, so it's important to understand that logarithms themselves are numerical values. Okay, so when I say log base 2 of 8, that is a numerical expression that has a value assigned to it. Okay, now in order to evaluate it, I think it's actually helpful to treat this like an equation. So I'm gonna set this equal to x, and we're essentially gonna solve for x here. Okay. So understand we're saying 2 to what power equals 8. So I've essentially gone from logarithmic form to exponential form here. I've now created an exponential equation, and we looked at these last section. To solve an exponential equation, you just try to write your bases on each side to be the same number? Well, 8 is 2 cubed, right? So now I have the same base of 2 on each side, and I can set the exponents equal to each other, okay? So that tells me that log base 2 of 8 is equivalent to the value of 3, okay? All right, next one, try to do it without all that work. Log base 3 of 81, it means 3 raised to what power is 81? That would be 4, right? Because again, 3 raised to the 4th power is 81. How about log of 100, or that's log base 10 of 100? So 10 to what power is 100? The answer would be 2, because 10 to the 2nd power is 100. Okay? All right, we keep moving forward. Now let's introduce to you a very special logarithm, okay? So last section we talked about the exponential function being y equals e to the power of x, right? Where e is that value of approximately 2.718, right? What if we want to find the inverse of that? Well, again, we would start with x equals e to the power of y, and then we would put it in its logarithmic form to solve for y. That would be log base e of x equals y. All right, now this logarithm, where it has a base of e, is known as the natural logarithm, and we have a special notation for it. So rather than writing log base e of x, we write ln of x, and it becomes y equals the natural log of x. Okay, so this is one of those things where it's, again, understood. If you see y equals ln of x, you really need to know that that ln represents log base e. They're one and the same. Okay, that would again be true if and only if x is equal to e to the power of y. All right, so a couple special natural logarithms. What's the value of the natural logarithm of e? Well, again, this is really the same as saying log base e of e, right? So e to what power is e? That would be the first power, okay? And then the natural log of 1, that would be the same as log base e of 1. E raised to what power is 1? The answer is 0. So the natural log of e is 1. The natural log of 1 is 0. Okay? All right, and then one more set of examples here. Here are a couple of logarithmic equations to solve. All right, so let's focus on the one on the left-hand side first. I would always begin, if possible, if there's only one logarithm in the equation, I would try to isolate the logarithm first, meaning get it by itself. Okay, so to do that, I would subtract 3 over to the right-hand side. So this is going to become 2 times log base 3 of 4x minus 7 is equal to 4. And then the 2 is multiplying the logarithm, so I'm going to divide both sides by that 2. That's going to take me to log base 3 of 4x minus 7 is equal to 2. And now from here, the logarithm is isolated, so I'm going to go into exponential form, which would be 3 squared equals 4x minus 7. Of course, 3 squared is 9. So you'll add 7 over 16 is equal to 4x, x equals 4. Okay. And there we have it. All right, now the next equation, this is an exponential equation that you're trying to solve. E to the power of 2x is equal to 5. And with it being exponential, I'm really kind of limited in what I can do to solve for that exponent involving x, right? So for this one, it would be beneficial to convert to your logarithmic form first. Okay, so if I do that, that would be log base e of 5 is equal to 2x. Log base e of 5 is equal to 2x. And a log of base e, that's the natural log, right? So this is really written as the natural log of 5 is equal to 2x. And this is very abstract because this is new to you, but understand that the natural log of 5, it really represents a numerical value. It's the value of e to what power equals 5, okay? It represents that power. We're just leaving it as the natural log of 5 right now because that's its exact form, its exact value. So I can solve for x here by simply dividing both sides by 2, and if I want to stay exact, I can just say that x is equal to the natural log of 5 divided by 2. That doesn't really mean a whole lot to me. Like I don't know what that value represents really, what it's really close in value to. So the nice thing about natural logarithms is they are programmed on your calculator as well. You have a button that has ln on it. So if you hit that and then type in a 5 and then close out your parentheses, then divide by 2, you should come up with an approximation of 0.805. Okay, so right there is kind of a more concrete, idea of what the solution to this equation represents.